Now we will get into the most useful part of this chapter, the equations of motion, also known as the kinematic equations. First, the simplest case, constant velocity or uniform motion. This means the acceleration is zero. The position versus time graph is a straight line, and the only equation we need is the displacement equals velocity times time. So just imagine if you're driving your car at perfectly steady 60 miles per hour. So that means you drive 60 miles for every time interval of 1 hour. Uniform motion is when equal displacements occur during any successive equal intervals. Uniform motion is always along a straight line. An object's motion is uniform if and only if its position versus time graph is straight line, which means the position of the object increased by equal distance for every equal, this is equal time interval. And the change of position for this object is equal for equal time interval. And the average velocity is the slope of the position versus time graph. The only kinematic equation we need for constant velocity motion is this one. Displacement equals velocity times time. What's the acceleration of constant velocity motion? Because there's no change of velocity, so acceleration has to be zero. There's no acceleration. Now we move on to constant acceleration motion. For constant acceleration, the instantaneous acceleration at any point in a time interval is equal to the value of the average acceleration over entire interval, which in other words, simply put it this way, acceleration is a constant. So acceleration has to be a constant over time. Now, by definition of acceleration is change of velocity over time interval. So we can have acceleration is the slope for the change of velocity. And because it's a constant acceleration, the slope and the velocity versus time plot has to be a constant. So the velocity versus time plot for constant acceleration motion is a straight line. Now keep in mind, for constant velocity motion is position versus time plot is straight line. For constant acceleration motion, is velocity versus time is a straight line. So we have our first kinematic equation for constant acceleration. Final velocity equals initial velocity plus acceleration times time. Let's look at an example. Let's say a car starts with a velocity of 2 meters per second to the right and accelerate to the right with acceleration 6 meters per second squared. Putting in the number and calculating, we find that the car will have a velocity of 40 meters per second after 2 seconds has elapsed. Because the car started with 2 meters per second, the acceleration is 6 meters per second squared. After 2 seconds, the speed or the velocity of the car increased by 6 times 2, which is 12. 12 plus initial velocity 2 give us 14. And the velocity versus time plot has to be a fixed slope, constant slope. Because the velocity is increasing or decreasing uniformly with time, we can express average velocity in any time interval as arithmetic average of initial velocity v0 and the final velocity v. The average velocity, this is also a kinematic equation. Keep in mind that the expression is valid only when the acceleration is constant, in which case the velocity increases uniformly. Let's combine this result with our definition of average velocity and set initial time to be 0 and the final time is t. Set displacement equals to delta x. Our result is the expression for displacement, which can be rearranged to give us the equation, kinematic equation as shown. We can make a substitution in our result for displacement using our equation for v. We got our second kinematic equation. So if we substitute v with the right hand side, so this is our v, put it all together, we get another kinematic equation. A key concept here is that the area under the velocity versus time graph is equal to the displacement. For constant acceleration, this area forms a trapezoid. And by calculating the area, we can derive our second kinematic equation. Displacement equals to the initial velocity times time, plus 1/2 the acceleration times time squared. So the red give us v0 times t, and the blue triangle part give us the change in position due to acceleration. So the red part give us the change in position due to the initial velocity. See, now I want to emphasize the concept that the area under the graph, velocity times time graph, for any object equals to the displacement of the object. Now we can do another replacement. From the first kinematic equation we learned, we can write t as change of velocity divided by acceleration. So displacement equals average velocity times time. Okay, now we can replace the t by this, what we have on the right hand side. And to do some algebra, we find displacement equals this. Rearrange this equation, we have our final, the last kinematic equation we want to show. By combining these ideas and doing a bit of algebra, we arrive at a set of equations for motion and constant acceleration. Those 5 equations are the tools we will use to solve most of our one-dimensional motion problems. We'll do some example in the next subsection.